Hello, everyone, and thank you for joining us here at Chromalox. Today, we'll be providing a presentation on sustainability and decarbonization through electrification. A lot of things to cover. We're going to talk about, what is considered sustainability, decarbonization. Obviously, here at Chromalox, we're electric heating options. We've got the largest breadth of product for all your heating needs. And there's a lot of initiatives going on in the world right now that we're a really nice fit for. So we appreciate everyone joining us. We're going to walk through those, and with us, and who's going to walk through that with us is James Lewis. James Lewis is our sustainability business development engineer. James.
My name is James Lewis. I'm the business development manager for sustainable energy with Chromalox. And with me as well, who did the introduction, is Derek DeBar, the energy sector sales and training manager. So together, we just wanted to dive into some topics centered around sustainability and decarbonization. Obviously, two topics that are very strong right now in the industry. And as Chromalox being leaders in electric heating technology and our focus on sustainability, we wanted to cover some of those offerings and solutions we have to address those conversations moving forward. So before I dive into really what decarbonization is and how we can have that solution, I like to get people grounded on what electric resistance heating is. So as you can see here, really the concept of electric heat and the technology has been around for about 100 years, but it's very simple in essence that an electric resistance heating element really is comprised of four main components: the resistor, which carries the current and generates the heat. You have an insulator material, which protects that internal wire, the metal sheath tubing, and then your cold pin and termination. So those four components are really all it takes for an electric heating element. But as simple as it is in concept, it's actually very versatile in how those elements can be used. You can see on the right-hand side there, you can bank multiple of these elements together to create very large loads, attachment fittings and tanks, vessels, you name it. So they're very versatile in that core technology. Now, typically what you see in the industry is low voltage technology, and that's basically anything that's rated up to 1,000 volts. But Chromalox has actually patented the first true medium voltage element, a while back, that's actually capable up to 7.2 kV capabilities. And we're going to talk about what really that is and why that drives the efficiency and the sustainability efforts moving forward. So again, kind of looking at the two technologies, not going to read it word for word, but you can see the major takeaways here on the low voltage side is that 95.7% efficiency compared to a medium voltage heater, which is nearly 99% efficient. So obviously from the operational side, there's a lot to take away from those increased efficiencies that the medium voltage gets you. But the other takeaway too, if you look at the 1 megawatt at 415 example there, that system would pull about almost 1,500 amps. An equivalent system at 6.6 kV pulls only 88 amps. So you can see just the drastic reduction that medium voltage technology allows for you. So if you take that again and apply that to another example, even a larger system at 3.2 megawatt, 380 volts, that's nearly 4,900 amps. So in conventional splits, that would require about 63 circuits of wiring. That same system on 6.6 kV pulls only about 280 amps. So you can see already, just by stepping up to that medium voltage electric technology, you've effectively eliminated 60 circuits worth of wiring, all the components, all the labor that goes into that. And then, of course, that's also why you get that improvement in your efficiency rating up to the 99%. So there's a lot of benefit you can realize both from operational and maintenance and labor by going up to those medium voltage systems. So while I can sit there and talk about those details all day, the picture definitely helps paint that a clearer picture for what that really means in the real world. So here's a 10 megawatt system at 600 volt, and you can just see all of the wiring and conduit that's needed to basically support that installation, that low voltage installation. So you can see just and imagine that you have to terminate those wires and cables both at the heater side and the panel. So it's a lot of components through the fusing and the contactors and all the labor involved in that. Versus here is a medium voltage system, same application, a little bit smaller, but still the concept holds true, that all that wiring infrastructure and components that's needed to support that is done in a very simple single conduit run. You can see there where the arrows are pointing. So it's much more clean. It's much faster to get these systems installed. And then, of course, the infrastructure that's needed to support those is drastically reduced. So when you kind of take all that and put it into really a summary of, okay, well, what is medium voltage really getting me from, the total picture? We can just see, one, again, we've trademarked the name. It's direct connect because, again, we can apply that medium voltage directly to the heaters. So you don't need those step down transformers. Because of the reduction in amperage, again, the infrastructure is drastically reduced. So all of the components and capital equipment is reduced as well. And then because the losses through the electrical system, which I'll talk a little bit in a few slides here, but because you have fewer components, you have fewer losses, and that's why you get that increased operational efficiency as well. So really from start to finish, that total cost of ownership of a medium voltage system is much more advantageous compared to what a low voltage system would look like. So really that's, again, the core of the technology and really the heart of what we're going to be talking about today, and really how we can, how we can address the sustainability and decarbonization picture with medium voltage. So while that's the technology, we ask ourselves, well, how can we apply that? So just like we see in low voltage realm with being, vertically integrated into immersion heaters and circulation heaters, boilers, you name it, those same heater types and styles can be accommodated with the medium voltage technology. So here's an example of what a medium voltage electric steam generator would look like. And we can see all the same pressure code standards with ASME, a pretty large range of pressures are capable with these systems. The heaters are third-party certified for US and international markets. So really, again, it's being able to adapt that medium voltage technology for all the same systems that are really in the market today. So we can see now where low voltage traditionally couldn't really breach into the larger areas, and that's where fossil fuels took over, and vice versa. The fossil fuels really couldn't get down to those smaller ranges. The direct connect medium voltage technology now is able to scale from the low realm where traditionally low voltage systems satisfied, and then scale that all the way up into the larger realm where fossil fuels typically take over. So it's a very dynamic and scalable solution that we have to address those decarbonization projects. So when we look at, when we talk about decarbonization, obviously we're comparing it to a technology. So really what we're looking at is how to break away from the fossil fuel reliance that we see. Not just in steam generation, but process heating as well. We see applications across the board in really thermal, any kind of thermal process of where fossil fuels are relied on this is where we can see electricity taking over now with medium voltage. The challenge has always been that, people really focus on, the cost of energy. Electricity is too expensive, gas is so cheap. How can we really see electric as a viable solution? And while that's true in the aspect that electricity is very often more expensive than gas, that unfortunately is a very narrow-minded look when we consider really the total cost of ownership. Cost of fuel is really just one aspect of it. So there was actually a study done by the U.S. Department of Energy Information Administration where they did just that. They evaluated the electric versus natural gas versus fuel oil systems to try to understand, what is the cost of energy and operation of these systems. What we saw, though, was that it was looking at nearly a 3 megawatt system operated at full load across basically the entire year, the 8,700 hours. What we know is that those systems in the real world aren't operated that way. It's very, it's not going to be operating at full load, and it's certainly not going to be operating at all times of the year. Instead, what we like to see is really, again, that total cost of ownership evaluation that factors in all aspects of the ownership, not just the cost of fuel. And that's where we start to see electric has a lot more of an advantage. So that's factoring in things like your thermal conversion efficiency, or how well does the system convert the energy into heat? Your operational efficiency, how well can that system respond to changes? Again, most studies look at it from a full load at all times of the year, but we know you have startups and shutdowns, turn down situations. So how effective can your system respond to those changes? Parasitic losses. So, once you convert that energy into heat, is all that heat used in the process, or is some of it being lost to the environment or other ways? So those parasitic losses can certainly impact the financial evaluation and the ownership costs that you see every year. Also maintenance costs. How much does it cost to keep up the systems? and tied to that is production downtime, is how often do the systems have to be maintained. Also, how complex are the systems? Are they more prone to unplanned shutdowns and failures? Because obviously that can be a big factor that comes into, cost of getting the systems back up and running or lost production, all of those things. So certainly something that should be considered as well. And then of course the capital equipment itself. And not just the steam generators, but what infrastructure from an equipment standpoint is needed, whether it's additional chemical treatments or flue stacks or just again, all that other equipment that's around that needs to support those installations. And then last is the emission cost. This is becoming a much bigger conversation where regions, countries, states, you name it, are starting to impose, financial responsibilities and costs associated with those emissions. So that's certainly something that has to get factored in. So now that we understand, okay, so if we look beyond just the cost of energy at an electric solution versus a fuel-fired, how do those systems stack up? We want to understand how does the electric, face those challenges against the fossil fuel systems. So looking at, again, those total cost of ownerships, we know thermal efficiency is a big one, is how well do the systems convert the applied energy into heat? And on the fuel-fired system side, typically you see those systems advertised between 80 and 90% thermal efficiencies. But it's important to realize that one, that's assuming ideal conditions, and that's also assuming a new unit. So as these systems operate, especially coal, coal fuel source, that you can get a lot of what's called soot that builds up on those elements, the heat transfer area, which basically reduces the capability of those systems to take that applied heat and put it into the process. So you lose some efficiency that way. And one thing that's not considered as well is the use of electric power to run these systems as well, because the blowers run through pre-purge and post-purge, runs to clear out those gases before the flames are energized. So there is some electric use that gets factored in. That's very infrequently is being factored into your total cost of fuel operations. So certainly something to be considered as well. So when you look at these systems and you say, okay, well, they're advertised at this, 80 to 90% efficiency. What is the true efficiency of those, the energy conversion? Typically, when you look at real world, it's going to be about 5 to 10%, below advertised, especially over the life of the unit. On the electric side, we can look and say, we know that thermal conversion of electric systems is 100%, meaning all of the power that's applied to that heater is converted all into heat. That doesn't mean there aren't losses. So the losses that we see on the electric side are upstream in your I²R, and that's typically losses through your power wiring, and then also heat dissipation through the power components. But despite those losses that are upstream from these electric systems, it still only factors in a few percentage of losses. And that's why we saw, again, earlier in that slide, about 95, 96 on low voltage and upwards of 99 on the medium voltage. So what that means is the ability to basically convert all that applied energy into heat, and the ability to control these electric systems on a 0 to 100 basis means we can use exactly the heat that we need. And typically that translates into a reduction in size of about 15% on average. So that's why in the title I put fuel-fired and electric systems are not created equal, because often we're looking at, again, those studies where a 3 megawatt electric system is compared to a 3 megawatt gas-fired system. In reality, that's not what we see in the real world. Is we know that these systems respond much better and are much more efficient, that we can actually have a smaller electric system than what the gas-fired counterpart might be. And then we also talk about operational efficiencies. So we know the fuel-fired systems do not operate at peak efficiency across all cases. Typically, these systems have about a 4 to 1 or possibly up to a 10 to 1 turn down capability. But by turning down these systems, you have to increase your excess air percentage to make sure that you have full combustion. That excess air is pulling heat away to the flue, and it's also diluting the streams. So there's a lot of efficiency that's lost when you turn these systems down. So again, getting back to the case where we're not operating 100% all day, we have startups and shutdowns and turn downs. We know that the true efficiency of these systems over any given day is much less than what the advertised efficiencies are. And I talk about the oxygen metering again with that excess air. You have to add that air to make sure that you have good efficiency of combustion, and you're not sending fuel right out the flue stack, because that becomes problematic from other aspects. So again, the increased air percentage just reduces those efficiencies. So really the takeaway there is if you're using a 10 million BTU boiler as an example, and you're operating it at 25%, because of that reduction in efficiency, let's say 60%, you might only need 2.5 million BTU, but in reality, you're still using 4.1 million BTU. So you're still using more energy than is required. On the electric side, if you need 2.5 million BTU, that 99% efficiency is going to get you using basically what you need at that point. So again, that factors into how these systems are controlled. So I've kind of alluded to it in a few cases here about the 0 to 100% turn down. Electric systems are very often controlled with what's called an SCR. Not to dive into all the nitty gritty and all the numbers, but basically these systems use proportional control, whether it be time-based or demand-oriented transfer. Basically all that means is that these things can shrink the time scale of how often the heater is on and off based on what your demand is. So if you have, say for example, 1 second cycle time where this system is evaluating how much power it needs, and it's saying I need 10% power, this heater is going to fire at 1/10 of a second, and then it's going to be off for 1/10 of a second. So you're basically using exactly the energy you need, not necessarily all of your power. So that's very important because we're able to basically reduce those energy costs, improve our efficiencies, and really just use exactly the power that's needed. And that doesn't mean, or that's not affected by your startup or turn down, because again, through all those conditions, if you have a lower demand, that system's going to basically respond accordingly. And it's very, basically on the 1 second time scale, as an example, these systems are very responsive and can basically change. Even if your system or process is very dynamic, it can evaluate that on a 1 second basis or even shorter, and basically output as needed. So again, very efficient with how these systems are controlled. Moving on, when you look at parasitic losses, again, just because you've combusted that fuel source into heat doesn't mean that that heat is being used in your process. So for fossil fuel systems, we know that after that combustion, a percentage of that heat is just lost right to the flue. So it's not doing your process any good. So you're spending money and energy to convert that to heat, but really all you're doing is you're sending it right out to the environment. So that's what we're considering a parasitic loss, is basically it's not doing you any good, even though you're using energy and using resources to create that heat. And it's also important to know too that it's almost a necessary evil, because you have to keep your flue temperatures above the dew point, because the last thing you want is that temperature to drop, and then all those harmful gases that are being emitted start to condense and then start to turn into more acidic, condensation that can actually wreak havoc on the system itself. So again, I call it a necessary evil, where you almost have to send some of that heat out to the flue to make sure that that temperature is above dew point. So it's parasitic, but it's necessary to keep these systems operating. On the electric side, it's very minimal, the type of parasitic losses we see. Just inherently with how the electric heating systems work, the elements are submersed in the fluid. So that means that the heat generation is being done within, which the heat has nowhere to go but into the process. So really the only parasitic losses you might see are on the exterior shells through heat losses. But traditionally these systems are insulated, and that prevents too much of those heat losses. So really we attribute this to about less than 1% is typically going to be lost from parasitic losses on the electric side. So from that aspect, you have a lot more energy savings, just keeping the energy where it's needed and the heat where it's needed, which of course is your process. We look at maintenance. This is a big factor for total cost of ownership as well. We know that we've already kind of alluded to it in some of the slides here, but the fuel-fired systems are much more complex with the burners and the fans, oxygen metering, the flue stack. Often you need chemical treatment because the internal coils are typically comprised of standard wall carbon steel, which obviously over time, if that wears away, that's problematic. So you need some sort of treatment on that. So there's just a lot more that goes into these fuel-fired systems, which means that it have to be maintained on more frequent basis. And also more complexity means more probability for error. So we know if there's a small failure, that might compound into other parts of the system, and that can lead you to an unplanned shutdown. So whether or not it's just planned maintenance to keep up with the systems, or it's just a failure due to the higher complexity, there's a lot more of a risk with your downtime, and it's just more time that the systems aren't operating, lower production output from that. So it's just, again, that higher complexity leads to higher maintenance. Also, these systems, because you're dealing with open flames, you typically need credentials with the skilled workers. So it's just more cost associated with getting the right people to work on these systems. With the electric side, these systems are much more simple. And then from a maintenance perspective, really, it's pretty straightforward with what we recommend. Obviously, you have your daily blowdown sequence, which again, that's not specific to electric. The fuel-fired systems should also have some type of regular blowdown maintenance. But from a monthly perspective, we recommend just inspecting the terminals for tightness, because that's going to be your one of the issues is the flexing from the heat and cooling that these terminals see is they can come loose. So that's just one thing we recommend is on a monthly basis, go through, retighten and check those terminals. Also on a yearly basis is removing the bundle and just inspecting for cleanliness to make sure there's not any buildup. But those types of checks can be done on the order of hours, not days or weeks like you see with any kind of larger failures that might happen on the fuel-fired side. So again, from the perspective of maintenance, these systems are much more simple. They can be worked on, and typically the failures you're going to see are going to be on commodity parts like fuses, contactors, things that can be replaced very quickly. So the takeaway here is the electric system allows you to basically have a lower cost maintenance schedule, but also keep the system up and running more days and more weeks out of the year, which basically means higher profitability. And then, of course, the capital equipment. I've already mentioned just all the infrastructure that's required to support the fuel-fired systems with the flue stacks and the oxygen metering, other chemical treatment that's needed. So even though the boilers themselves are traditionally lower cost than what an electric, an equivalent electric system would look like, all the infrastructure definitely helps to shrink that gap between the cost of the actual electric steam generator itself, because there's just a lot more that's required to get these systems up and running. And again, on the electric side, just much more straightforward in terms of that capital equipment. And most of the capital equipment that's required is really the same for the fuel gas as well. When you look at blowdown tanks, feed systems, condensate returns, that's not specific to electric. So when you really look at what is specific to electric, it's a drastically simpler infrastructure that's required. And then this is again, I mentioned it, this is a bigger talking point now as we're starting to see more countries and more regions and states imposing these types of carbon credits and carbon taxes. We see that now, especially major offenders, if you're going to be having a lot of combustion sources at your facilities and you're going to be emitting a lot of CO2, many states have thresholds that are going to be imposing these taxes and cap and trade credit policies on them. So if you look the gas-fired system as an example, you can emit 465 tons of CO2 for every 1 million BTU each year. So, and 1 million BTU really isn't that big. So even just, a 10 million BTU, you're looking at just under 5,000 tons of CO2 a year. And most of the thresholds that are set by states, if that is their policy, really isn't that much higher than that. So it doesn't take much to get yourself into the threshold where now you're going to be, you're going to have some of these policies imposed upon you. So just using an example, okay, what does that translate to, factoring in my total cost of ownership? How much is this going to cost me? We know, $25 a ton of CO2 as an example, looking at the state of Washington where they're looking at $25, that's almost $12,000 for every 1 million BTU a year. So these charges certainly can stack up. I was actually talking with a company that was evaluating their facility. They were actually paying $65 for every ton of CO2, and their emission level had them, at thousands of tons of CO2 a year. So they were paying over $1 million in these carbon taxes and carbon credits. So it's certainly something that it's a very real cost if you're located in a region that has these types of policies. And it's something that, of course, with the electric side, we don't have those combustion sources at the scope 1 level. So we can help your facilities basically get under those thresholds or eliminate those altogether by eliminating those combustion sources. And then even if you're not in a facility or a state or a region that has the CO2 policy, one thing that always has to be factored in as well is your facility's air permits. This is basically looking at hazardous air pollutants and emissions outside of CO2. So this would be like your NOx or your sulfur dioxides, particulate matter, or other volatile compounds. Basically, all those other emissions that are happening can be factored into your air permit for the facility. Now, most of the states and regions have thresholds. If you by chance do cross into the major source, otherwise called a Title V permit, These are very cumbersome into basically maintaining these on an annual basis, both through administrative and record keeping, different audits that have to happen, maintenance fees. They can be very cumbersome, not only from a financial perspective, but just time to keep up with these types of evaluations. So if you do fall into the Title V threshold, just using, again, the West Coast as an example and how these states price these, that could be on the low end of $30,000 a year. On the high end, I've seen upwards of $300,000 plus just to keep up those Title V permits. So again, that's excluding CO2. That's everything else that these combustion sources can emit. So the big takeaway here, again, from an electric perspective, when you're looking at decarbonization and looking at more sustainable solutions, and especially with what Chromalox offers with the medium voltage side, is you don't have to necessarily decarbonize the entire facility. Sometimes just getting yourself below the thresholds from that Title V into a minor source can realize a lot of benefits, both financially, but also towards your sustainable initiatives. So whether or not that's just a short-term solution, just starting small and trying to get below some of those thresholds, or just realistic in terms of what capital investments available to you, or resources. Again, you don't have to necessarily decarbonize an entire facility. You can still realize very major benefits just by decarbonizing certain aspects of the total facility. So again, just something to be aware of with a lot of the policies that are starting to come out, and really how the electric solution, especially the medium voltage, is now bridging that gap into the fossil fuel realm. We can see that we do have that solution to help your efforts. So we take all that, again, that was a lot to run through, but we take all that and we kind of circle back to that evaluation of, hey, the cost of electricity is too expensive. We see, well, not really. If you look at the real world of how these systems are operated, we know that they don't operate at full load for the entire year. There's a lot more dynamic, these systems are operated much more dynamically. That the actual costs attributed to it, especially when you factor in the total cost of ownership, now becomes much more advantageous for the electric solution. So, not to focus too much on the numbers, because there's a lot of variables. Every facility is different, but the big takeaway is that really there is a deeper picture beyond just the surface evaluation of that cost of energy. So we do have, again, with that medium voltage technology, we have a way to address those concerns and issues and give you a viable solution for the decarbonization that your companies are looking to do. That was a lot to run through. Now, kind of getting everyone grounded on, what our solution is, what electric heating and medium voltage is, and then how that factors into a comparison to fossil fuels. Now I'll turn it over to Derek to give you a little bit more of a real world and case study basis to run through. So Derek?
No, I appreciate that, James. Kind of as you mentioned too, right, with the government and state, I mean, that it can seem overwhelming, but honestly, just getting below the thresholds and a lot of real, I call them small impacts, can mean a lot to not being held to the Title V or the considered major offenders or polluter scenarios. A couple things to touch, and a couple of real life scenarios that I kind of want to walk through with everyone is how to start chipping away at this throughout industry. You could be in various markets, all facing the same issue of these pending air permits and fines and new regulations that are coming into play, especially in 2022. So to touch on that, I'm going to kind of walk through these little scenarios and solutions that Chromalox has available today. We can talk to you about this tomorrow if you reach out to any one of our representatives or direct people, or James and myself. A couple things to look at, and James touched on these. That photo at the top is to kind of give you a scenario. The thermal efficiencies of electric heaters is much more efficient. We're still applying heat, but how they operate is a little bit differently. We're still doing the heat transfer, but they're, as James had mentioned, the flue and the parasitic losses are not the same. So those factors play a lot into these solutions that we have. So whether it's your piping to and from your process, your electrical heat tracing, to gas-fired, boiler scenarios, or fire tubes, as we call them, to even duct heating applications, and we'll walk through these examples here to kind of get you thinking of solutions that exist today and how to chip away at these regulations that are coming through. So moving on, heat tracing specifically, we've had actually several really interesting applications and installations recently through that utilize our products specifically. We have this unit. It's a centralized power connection kit called a DTS, which is digital thermostats. All that stands for. But the unique, interesting thing about this is the third parties are written around. They can be used on anybody's heat trace. So you think of installations that already exist. You can apply this. It's even been written into some federal and state regulations to have point of use control. A lot of larger heat trace systems that are installed today at whether power plants, oil and gas, chemical facilities, they run on a central control system where it kicks everything on at once, or everything off depending on if it's freeze protection or process control. You can now go in and retrofit with these units, and now this would have impacts, one, to your line loads. You get point of use control. It's really good for meeting some of these sustainability goals. Electrical heat tracing in general is a good alternative to maybe a heat transfer system or steam tracing. So if we got installations where you're doing expansions or looking at an alternative to what you're doing now for your line heating, our heat trace product line fits very well into sustainability goals and can have quite an impact on whether you have an install base or whether you're looking to expand. Some of the other impacts that we have available, if you can, so think of your gas burners, traditional gas, fossil fueled. We mentioned a lot in some of our presentations about API 560 boilers, but these could be fire tubes. There's ones through steam generators, all basically operating the same, right? You have your fossil fuel fired burners, you're transferring heat through a series of exchangers or fire tubes. But as James mentioned earlier, the flue has to be hotter. There's a lot of losses. Your heat efficiency is not quite there. The electrical equivalent to that, one, has a smaller footprint, which helps you, but your low area classifications and stuff, a lot of times we can now put these at point of use. They're much more compact. There's no burners, no flames, and again, they're electrical, so no emissions. So they're a really good alternative. And you will find that there are more incentives beyond meeting sustainability goals and even monetary impacts because of the efficiency of these units. And we're getting on a much, much bigger scale with our direct connect technology and medium voltage, which is unique to us as well. Taking that a step further, there's a lot of, and we're talking to governments, we're talking to municipalities and utilities around. There's district heating, facility, building heat. Big centralized boilers are now coming offline, and they're looking at replacing them, and in some cases are replacing. Not even looking. We have orders in house to replace their central system with an electrical equivalent. It's obviously much smaller footprint. We can locate it, point of use. We talk about decentralizing options. So take out your large heating system. If you're on the threshold of meeting or being considered a major contributor to, getting your air permits and all that, we have options to maybe take, you have multiple burners, multiple water heaters, depending on your application. Small impacts, maybe just replacing, a 2 or a 4 or a 5 megawatt installation will now take you down and out of those larger air permit costs. James had mentioned Title V and those type of things. We have those options already commercially available to be installed. You just need to contact us and we can walk you through how the function's the same, kind of the fit in the application's a little different, and we can certainly explain how those fit into your applications and the impacts they can have financially and on your air permitting as well. A couple other options too, definitely things to consider that don't necessarily come up as often, are air heating, duct heating. You got big gas-fired systems, not only for commercial and we'll say facility heating, but also in industry. There's drying applications in mining. There's intake heating, where traditionally a fuel-fired system is the standard. It's what we're used to. It's what's been installed for 50, 100 years. But as these regulations come into play and more impacts to the end user or the facility owner, you really want to consider maybe there's an electrical option, which we already have readily available. Quite frankly, our duct heating has been around for a long time, but hasn't been properly utilized, in my opinion, in industry. And as the electrification of things comes more and more to the front lines, our electric heaters, even our traditional designs like you see here that have been available for a very long time, are more appealing and now affect those sustainability goals. We also have, with our medium voltage designs, we can go up to much higher higher outputs. And then we have open coil, right, for efficiency. So all of that is available and has been available for some time. This one, and we get this a lot, your indirect heating. So you'll have a heat exchanger, a jacketed vessel, especially in your chemical markets, your your process facilities, your process heating with heat transfer fluids. You can now take your large system offline and go with these small compact units that utilize electric heating technology here at Chromalox, where you're adding a blower or a pump and your controls and all these nice packaged units that become modular. You now put them at point of use. You can now individualize your system and make those small impacts along the way in your facility. And it really doesn't take a lot of engineering time or design time. A lot of it's plug and play when you start considering going with an electric option. And then, just to give you an idea of scale, our medium voltage technology, which, when we say medium voltage, we're talking 4160, 7200 volts, so your transmission lines. A barrier to this in the past has been, the power distribution, stepping it down to a more usable voltage. 480 is a standard in a facility, or a 208, a 277. That's not the case anymore. This is direct to the element in the Chromalox design. It's been commercially available for almost 10 years. And then we utilize our history of designs. We've got high pressure, we've got steam generators, and it's not a new technology for everyone as much as it's just packaged and used more efficiently for these applications. And now that decarbonization is the focus and sustainability, it's more relevant than ever to utilize our products and to make an impact to your bottom line, to make those small impacts of your facility in the discussion today. And then, finally, to lead with a couple other things that are most readily available for us. We are Chromalox. We do tank heating quite well. Speaking of those small impacts, we have all options available from directly heating a tank to heat tracing a tank. You got your screw plug with integral controls. We can do the high pressure ANSI flanges, the over the side. And to kind of give everyone an idea of the variety of small impacts we can have based on, your tank, your facilities, your feedstocks, all these little impacts all add up to your bottom line. And the reason I show these is on the next slide, the real impacts that we're seeing out there. Traditionally, a lot of this tank heating and stuff, it's kind of forgotten about, and then it adds up. So then you have not one, not two, not three, you have multiple fire tubes or these fossil fuel fired options that really add up. And then back to what James was saying, those costs are now starting to impact. When you get to a certain threshold, the financial impacts are significant. So if we can start looking at or thinking of your facility and making these small impacts today, you will start chipping away at it and become more sustainable. I use this example just recently. We've been talking about these for years, about replacing the traditional fuel-fired tank heaters and separators and those processes with electric heaters. And what we found out just recently is this year, finally, that discussion has come to the forefront that we want to make these small impacts, and end users are now open to that because they need to, especially financially. The substitution, and you can see that on the bottom of the electric units, and James touched on this, it's far more efficient of applying the heat and control, you can wire it into your building management system. You can control it. And so now you're saving money not only by efficiency, but now you're not having a carbon impact. You don't have emissions, and you can start, like I said, to chip away at a lot of these options that are already available with Chromalox. We just need to work through your process and explain how they fit together. So I thank you all for joining us. I really apologize for the mic issues at the very beginning, but we got that worked through. James is about the best resource I could think to talk about any of these sustainability and decarbonization options that you have out there. And with that, we'll open it up for questions. Please type those into the chat and we can address those. But James, nice work. And I appreciate anything else you'd like to comment or say here as we close out.
No, I appreciate it, Derek. And yeah, it's a lot to run through, a lot to wrap our heads around. But as you mentioned, certainly I'm available if there's any questions or even just reaching out to local Chromalox representatives. We can certainly all work with you on identifying what your goals are and what the right solution is. And I don't think I missed, or I don't think I mentioned it. I've kind of crossed over it, but we certainly do have some tools to help you evaluate what those total cost of ownership evaluations and emission levels look like. So if you're trying to understand really, is it feasible for me now, or what is the right solution, feel free to reach out to us and we can certainly work with you on that using some of those tools. So thank you again, Derek. Appreciate the time.
And thank you, James. And along with those tools, please utilize our local representatives, because we'll have examples where other folks in your industry have already tackled or applied the electric heating options to start working towards sustainability and decarbonizing your facility. So, James, thank you very much. Good job. And appreciate everyone's time. And thank you all.